Public ledgers broadcast transaction intents in plain text before they are executed. This structural flaw exposes every impending trade to any node monitoring the network. This transparency directly enables MEV, or maximal extractable value. This is the profit that network operators and searcher bots extract by reordering or front-running pending transactions based on their visible contents. In a secure system, a transaction payload would remain encrypted, remaining opaque to searcher bots until a specific execution condition is met. Because these networks default to radical transparency, complex financial structures like sealed bid auctions and institutional dark pools cannot function securely on-chain. Scaling open finance requires a method to maintain verifiable consensus while preventing information leakage. A common industry assumption is that ZKPs provide a complete solution for on-chain privacy. Zero-knowledge proofs are a cryptographic method allowing one party to prove a statement is true without revealing the data behind it. However, they do not provide pre-execution privacy. ZKPs are designed for execute once, verify everywhere, proving the integrity of a completed computation. But they hit a structural dead end when a protocol must compute directly on a hidden state, rather than verifying a past action. Executing logic on hidden data requires an entirely different mechanical link in smart contract architecture, conditional decryption. Protecting user intent means moving past verifiable computation and engineering programmable, conditional privacy. Protecting every transaction requires a multimodal cryptography stack. Using a single heavy cryptographic method for every action would cripple network throughput. To evaluate the trade-offs, we can map these primitives on a matrix comparing their computational overhead against their conditional complexity. For temporal conditions, we rely on Threshold Identity-Based Encryption, or tIBE. In tIBE, the public key is derived from a known identifier. A minimum number of participants must cooperate to derive the final decryption key. It bypasses complex key generation by using an arbitrary string, like a future block height, directly as the public encryption key. To prevent premature revelation, the network utilizes a threshold mechanic. Decentralized validator nodes generate independent mathematical key shares tied to a target block. Once the threshold is met, these shares aggregate to produce the decryption key for the ciphertext. Because the key generation is decentralized, no single validator or rogue entity can derive the key and expose the transaction early. Its low computational weight makes tIBE the optimal mathematical primitive for high-frequency, time-locked events, like shielding trades from MEV extraction. Time locks are predictable, but conditional decryption becomes architecturally difficult when the trigger is an unpredictable market state, like an asset reaching a specific price. Looking back at the matrix, we solve state-based triggers using witness encryption. Witness encryption ensures a message is decrypted only by providing a valid witness to a specific statement. Under this model, the payload is cryptographically bound to a state-dependent statement, such as a price threshold. The message remains encrypted until a specific witness is broadcast to the network. That witness is strictly defined as a valid cryptographic proof, demonstrating that the mathematical statement now evaluates to true. In academic cryptography, witness encryption is functionally equivalent to a laconic, special honest verifier zero-knowledge argument, or SHV-ZK. An SHV-ZK is a zero-knowledge protocol where the proof is short and assumes the verifier follows the protocol exactly. Because of disequivalence, the decryption process is directly triggered by the verification of a standard ZKP. By bridging pre-execution privacy with established zero-knowledge frameworks, witness encryption enables secure, state-dependent on-chain triggers. The highest level of cryptographic complexity occurs when data must be computed without ever being decrypted by the operator. On the matrix, this is Threshold Fully Homomorphic Encryption, or tFHE. tFHE is a scheme allowing direct computation on encrypted data, requiring a distributed threshold of keys to decrypt the final result. It allows algebraic operations, like addition and multiplication, to be executed directly on the ciphertext. In this model, two distinct ciphertexts enter an arithmetic gate, combining to produce a new encrypted output. The operator processes the data without knowing its values, producing a mathematically accurate result. The end user then decrypts the final result to reveal the accurate sum, while the original inputs remain completely hidden from the network operator. The trade-off is a severe computational bottleneck. The complex algebraic operations generate massive mathematical noise and significant processing overhead. To overcome processing limits, the industry relies on advanced hardware acceleration, utilizing photonic technology and customized ASICs designed specifically for intensive cryptographic computation. Because of this extreme computational cost, tFHE is reserved for operations that demand absolute mathematical privacy during the computation itself. Decentralized privacy depends on a specific routing architecture. This diagram shows a unified API parsing an incoming transaction intent. It analyzes its specific conditional requirements before assigning the cryptographic method. The coprocessor orchestrates the transaction. It routes temporal conditions to tIBE, state-dependent logic to witness encryption, and hidden mathematics to tFHE. A decentralized application-specific blockchain handles this orchestration, functioning as an independent oracle for decryption keys. By offloading the key generation and routing to a dedicated coprocessor, the host network avoids the latency associated with heavy cryptographic processing. This modular approach to cryptographic selection enables the creation of markets resistant to manipulative information leakage. Mitigating MEV and information leakage makes institutional-grade dark pools and sealed bid auctions feasible on public ledgers. Programmable privacy secures these transactions while maintaining the trustless, decentralized nature of the underlying blockchain. Developers no longer have to choose between scalability and execution privacy. Matching the precise cryptographic primitive to the exact state transition requirement enables conditional execution without exposing the underlying data.